Dos, tres.
Good afternoon. We are Team 7 integrated by Marco Antonio Barreto and Gary Lara, and we're going to talk about the Delivery 5 of our final project. As a brief introduction, our project talks about the Zapotlan Lake, which is the second largest lake in Jalisco. The stattal authorities regularly monitor this lake in 4 sampling points, collecting data from about 70 variables, water quality variables, which tell us how the lake is going, exactly if it is safe for the species to live in there or for the population near the lake. The variables that we select are the biochemical oxygen demand, which is BOD, and the total solid suspended, which is TS. These are continuous data generated by measurements of natural values, as we already said. And these variables in our hypothesis are divided in levels according to the lake location, which is the sampling points, one of the 4 that we already mentioned, and also by time frames from one milestone to other, such as the introduction of water treatment plants, of the change in the agricultural type activities. The next, please. This is the summary of the data for the BOD and the TS. The next. For the distribution identification, we started variable. As we can see in this table, we use the R-risk distribution package in R. The log normal, it represents the major log likelihood value. But as we can see in the next slide, its QQ plot was very close to a straight line in the log normal case. And the gamma distribution, which was the second largest log likelihood value and has a very QQ plot, and also by the definition of the event, which gamma constitute the sum of k independent exponentially distributed random variables. And also in the literature, we read that the gamma distribution is widely used in environmental modeling situations. So we decided to stay with the gamma distribution for the BOD. For the TS, as we can see in the table, the log normal represents the major or the largest log likelihood value, and also precise or very similar QQ plot behavior to the straight line. And also, since the log normal is a continuous variable, which logarithm of the data follows a normal distribution, we can use it to model this variable, which is TS. That's how we select the distributions.
Okay, then for our scientific hypothesis, we have 3, and is that the first one, the lake location has an effect over the biochemical oxygen demand variable. The second one is that the time over the years has an effect over the biochemical oxygen demand variable. And the third one is the introduction of sewage treatment plants around the lake, and it has an effect over the total solids variable. For our first hypothesis, scientific, we have the first statistical hypothesis, and it says that there are no significant differences between the average biological oxygen demand among the lake location. And the alternative hypothesis states that there is a significant difference between the average biological oxygen demand among the lake location, as we can see here in the statements. And well, for the number 2, we have that statistical hypothesis number 2, that the null hypothesis states that there are no significant differences between the average total solids concentration among periods with different agricultural activities. And the alternative hypothesis states that there is a significance difference between the average total solids concentration among periods with different agricultural activities. And for our third statistical hypothesis, it states that there are no significant differences between the average biological oxygen demand amongst periods with different presence of water treatment plants. And the alternative hypothesis states that there is a significant difference between the average biological oxygen demand among periods with different presence of water treatment plants.
Okay, for the outlier identification and determination, we consider as the hypothesis, since we are or by an hypothesis or by a hypothesis approach, sorry, considering that each level should be in mean and variance or in theory different to each other, we do box plot for each level. For example, we have the first statistical hypothesis, which is the BOD concentration at each sampling point, 1, 2, 3, and 4. And we have a box plot for each of these levels. And then we identify that we have only one outlier in the level 2. This was corroborated by the calculation of the interquartile range. The next. For the second statistical hypothesis, which is BOD in time frame 1 and time frame 2, we have 2 outliers in the time frame 2, which are those points of the box plot. And for the third hypothesis, which is the TS, the total solids and time frame 1 and 2, we don't have any. These outliers, doing a little research, could be due mistakes in the sampling, or also as since the lake is open at the environment, any environmental event or phenomena such as rain, such as wind flow, could affect these measurements. But since we don't have any certainty of this, we decide to keep these points to avoid losing this information and variation of the variables.
And well, for our first scientific and statistical hypothesis, we have that our variable follows a gamma distribution, and we want to compare the means of the 4 different stations around the lake. For that, we calculate the MLE and the Kramer raw lower bound. And as a first step, we take the likelihood of the PDF, as we can see here, for the gamma distribution, which is the product of set function. Then we obtain the log likelihood, and we simplify with the log properties until we obtain this expression over here. Then for simplification purposes, we fix alpha, and we are going to see how beta varies. So we derive in terms of beta in this first derivative to obtain our statistician beta hat for the MLE, as we can see here. And for the Kramer raw lower bound, we find the Fisher information by doing the second derivative of the log likelihood with the respect of beta. And then we apply the inverse to find the Kramer raw lower bound. We obtain that the MLE for beta follows a normal distribution with a mean beta hat and a variance with the Kramer raw lower bound. And well, in this plot, we can see the comparisons of the 4 different stations. And we can see that the means are close to each other. They are only decimals apart. And we can also see that from station 4 and 1 are similar in shape and close to each other. And this could suggest us that there are more organic contaminants around those areas than in station 3 and 2. The last observation is that these 4 curves have a high peak, and the area under the curve is really small, as we can see. And so the variance for the MLE should be very small as well. So for 40 observations, as expected, the Kramer-Rao lower bound for all of the 4 stations is really small, almost close to 0, as we can see, as expected. And this leads to a small bias as well, as we can see over here for the MLE. Well, for our third statistical hypothesis, we have the same variable, which is a biological oxygen demand, and we are going to compare it in between different time frames. And in this plot of the MLE for the hypothesis 3, we can see that the mean of the oxygen in the water is really low in comparison to the time after the sewage treatment plants were installed. So where the oxygen in the water is increased, we can see here that the oxygen is pretty high over here, and it's low over here in comparison with these two. And we can also see that the area under the red curve is really small in comparison to the green curve. So the variance will be near to 0, smaller than the green one. For 30 observations, we can see that, as expected, the lower bound for the 2 time frames is near to 0. And the green lower bound, as we can see here, is greater than the red one in numerical. And well, for the last statistical hypothesis, we are going to see the PDF Lognormal for the solids concentration, and we want to compare the means in between time frames. So for that, we follow a similar process to obtain the MLE and the Kramer-Rao lower bound for the Lognormal distribution. We find the likelihood, then the log likelihood, we find the first derivative, and we obtain the MLE for a statistician, our expected value there. And then we look into the Fisher information and find the Kramer-Rao lower bound. And then we obtain the MLE for mu that follows a normal distribution with mean mu hat, and a variance with the Kramer-Rao lower bound. And well, in this plot, the MLE for the hypothesis 3, we can see that the solids in the water is greater in the period for agricultural activities, which is from 2009 to 2013. And with the introduction of other types of agricultural activities, such as the greenhouse houses, shows a drop on the solids in the water, as we can see from 2014 to 2019. And again, we have small areas under the curve. And so for 30 observations, the Kramer-Rao lower bound is really low for both of them, closer to 0. Yes.
Well, for the last part, which is the exponential family, we started with the gamma distribution that is followed by the BOD variable. We start with the density function, we can see here. Then we rewrite the previous expression, these density functions, in terms of exp and logarithms. We do a rearrange here to divide this into the structural form. Here we have the HS and all these variables, the ones that are directly related with X and with the parameters. And then we transform it to the canonical form. From the log partition, we obtain the etas definition. Here we have alpha and beta, defined in terms of etas. And then we substitute this in the log partition. Here we have from this to this by substituting alpha and beta. And then in order to determine the expected value, we obtain the first derivative from respect to each parameter, alpha and beta respectively. Here we have it. From respect to alpha, we have the phi gamma function minus log of beta. For beta, we have alpha times beta. For the variance, which is the second derivative of the log partition in the canonical form, we have this, the second derivative respect with eta 1, and this with beta, the second derivative respect with beta. And here we have the results, the variance. And finally, for the covariance, we have this log partition in canonical form, but with the derivatives for the eta 1 and eta 2. And here is the result beta of the covariance. This is for the gamma distribution. For the log normal distribution, we start the same from the density function, which is this. We rearrange this in the terms of exponential and logarithms. Here we substitute this. We do a simplification here. From this term, we subtract this outside the equation to be hx. And this, we rearranged it again. Here we have the tx, sufficient statistic, the log partition, and then we proceed to transform it to the canonical form. Here we have the definitions of eta 1 and eta 2. We have the definition then of sigma square and mu. We substitute this into the log partition here, and we have this. Then, as in the gamma function, we proceed to do the first derivative and with respect to each parameter to determine the expected value. Here we have with respect to sigma square, and this with respect to mu. And for the variance, which is the second derivative with respect to each of the factor of the parameters, here we have for the eta 1, we have the result, and for the eta 2, we have this result. And finally, for the covariance, we do the derivation with respect to each of the parameters, and this is the final result. So that will be all for our part. Thank you for your attention, and stay safe.